Today we are going to discuss first law of thermodynamics. Now see, in case of first law of thermodynamics, or before going towards the first law of thermodynamics, let us know the meaning of thermodynamics. This thermodynamic word, that is, it is nothing but the combination of two different words. One is therm and another is dynamics. That means the literal meaning of thermodynamics is nothing but therm is heat and dynamics means motion. Means how the movement of heat takes place, that we are going to discuss in case of thermodynamics. Now, before going to know about the statement of the first law of thermodynamics, let us define thermodynamics. What is thermodynamics? Now, thermodynamics is a branch of science which deals with the study of interconversion of heat or flow of heat or energy into or out of the system due to physical or chemical transformation. Now this is thermodynamics. Means in thermodynamics what we are discussing? We are discussing about the interconversion of heat into other forms of energy. Now in case of this first law of thermodynamics, the next one is macroscopic properties. You might have heard about the microscopic properties, but in thermodynamics we are mainly dealing with the macroscopic properties. What are macroscopic properties? The properties which are associated with macroscopic system, that is consisting of large number of particles, are called as macroscopic properties. Now these properties are pressure, volume, temperature, density, viscosity, surface tension, etc. Knowing about what is thermodynamics, the next is one must know the terms, basic terms in thermodynamics. Now these are the two main terms in thermodynamics. The first one is system and second one is surroundings. Now thermodynamically, whatever you are discussing or you are studying, now that becomes a system and the rest part is surroundings. Now see, we will know the systematic definition of system. What is system? Now system can be defined as any specified portion of matter under study which is separated from the rest of the universe with a specified boundary. For example, suppose if you want to discuss about this marker. Now thermodynamically this marker is a system, one system. Now which is a specified portion of matter under our study and which is separated from other parts of the universe. That is system. Then what about the surrounding? Now leaving this marker, this is a system. We want to study or we want to discuss about this marker, the rest of the part is surrounding. See how we can discuss systematically. The rest of the universe which might be in a position to exchange energy and matter with the system is called surrounding. Now surroundings, we can quote example for the surrounding like air, water, in which a system undergoes examination. After knowing about the basic terms of thermodynamics, system and surrounding, now next one is types of system. Now there are three different types of system: open system, closed system, isolated system. Now these three different types of systems can be classified on the basis of exchange of heat from system to surrounding. Now see, the first one is open system. What is open system? It is a type of system in which or the system which can exchange matter as well as energy with surroundings. Example for this open system is, suppose if you take a beaker, in the beaker you take water, therefore this water when you keep in the atmosphere, what happens? The water can be evaporated. When the water can be evaporated means whatever the amount of water present in the beaker, that is matter, and for that evaporation process some amount of external source is required, that is energy. That means with the evaporation of water the amount of matter affects, and to evaporate the water the energy is required. That means in case of open system, now energy as well as matter both can be exchanged from system to surrounding. Now second type of system is closed system. Now this is also a kind of system or type of system in which can exchange energy but not matter. Example for this closed system is again the beaker containing water, but this is closed one. Now in this case what happens? What is the definition of closed system tells us? A system which can exchange energy but not matter. Means whatever the amount of water present in the beaker cannot be exchanged, but when you keep this closed beaker into the atmosphere, what happens? If you touch the surface becomes hot. Why? Because there is exchange of heat from system to surrounding. Now the third kind of system is isolated system. This is also a type of system in which neither energy nor matter can be exchanged from system to surrounding. Example for this isolated system is the beaker containing water but which is insulated. Not only closed but also insulated, means there is no chance of exchanging heat from this inside beaker to the outside. That example for this isolated system we can quote thermos flask. The next part is process. There are two types of process, isothermal process and adiabatic process. Now let us know what these processes are. See, the first one is isothermal process. A process is said to be isothermal if the temperature of the system remains constant during each stage of the process, that is delta T is equal to 0. Means what? Suppose let us consider a chemical reaction. Now that chemical reaction takes place in a vessel which is not insulated. The system is thus in thermal equilibrium with the surroundings. If the process is exothermic, that means heat is evolved the process, then this heat is given out by the system to the surrounding. Now instantaneously the temperature of the system therefore does not rise at all at any stage of the process, that is delta T is equal to 0. Now the next one is adiabatic process. A process is said to be adiabatic if no heat enters or leaves the system during any stage of process. That means suppose here also if you consider the chemical reaction in a vessel which is insulated. Now if it is insulated, means what happens? No heat can leave or enters the vessel from the surrounding. If the process including a chemical reaction which is exothermic, the heat evolved remains within the system and therefore the temperature of the system rises. That means there is no exchange of heat during the process. Is the first law of thermodynamics. Statement of the first law of thermodynamics. Now first law of thermodynamics states that energy neither be created nor be destroyed, although it can be transformed from one form into equal amount of another form. Means what? Now this law is also known as law of conservation of energy, means energy is conserved. The energy of universe remains constant, that is we can say the first law of thermodynamics, that is nothing but the energy is conserved. Now whenever energy in one form disappears, now an equal amount of energy in some other form appears. Now suppose let us consider a system. In that system the system is changes from state A to state B, which are having the internal energies EA and EB. Therefore change in internal energy for the system delta E is equal to EB minus EA. Now this energy change is brought about by the evolution or absorption of heat, and some amount of work is done by the system. Now if a system changes from state A to state B, it absorbs some amount of heat, that is Q, and from surrounding, and do some amount of work, that is W. Therefore change in internal energy in this above process or in this above system delta E is equal to EB minus EA, which is equal to Q minus W. If in the given process the quantity of heat transferred from the surrounding to the system is Q and work done in the process is W, therefore change in internal energy delta is equal to Q plus W. Therefore this is the mathematical statement of first law of thermodynamics. Now here there are two sign conventions of this work done. Now see what are these? That is before this we have discussed delta is equal to Q minus W, and here it is delta is equal to Q plus W. Now these, that is the positive and negative sign of work done, these are coming under the sign conventions of work. What are these? That we will discuss here. Work is done by the system on the surrounding, then we have to take W sign is negative, that means during the expansion of a gas. And work is done by the surrounding on the system, the sign for W is positive, that means compression of gas. Part is reversible process and irreversible process. Now see what is reversible process. A thermodynamic reversible process is one that takes place infinitesimally slow and its direction at any point can be reversed by an infinitesimal change in the state of the system. This is reversible process. Means reversible process is nothing but at the equilibrium stage. It can be reversed from both the directions. Now what is irreversible process? Irreversible process is one when a process goes from initial state to final state in a single state and cannot be reversed, cannot be carried out in a reverse order. This is irreversible process. Now in case of irreversible process, the system is in equilibrium state in the beginning, not at the point. This is irreversible process. Next part is, which is the important one, that is the expression of work done in an adiabatic reversible expansion of an ideal gas. Now to derive this equation, we have to consider, see, this is the adiabatic process. For adiabatic process, now PV raised to gamma is equal to constant. Now differentiating this equation 1, we will get P within the bracket gamma into V raised to gamma minus 1 bracket close dV plus V into dP is equal to 0. Now the same equation after simplification, see here gamma into PV raised to gamma minus 1 dV plus V raised to gamma into dP is equal to 0. Equation number 2. Now this dividing this equation 2 throughout by gamma raised to V raised to gamma minus 1. Now if you divide with this, what happens? We will get gamma into P dV plus V dP is equal to 0. Therefore V dP is equal to gamma minus gamma into P dV. This is equation number 3. 1 mole of ideal gas, PV is equal to nRT. If we differentiate this equation 4 completely, we get P into dV plus V into dP is equal to nR dt. Now see here, putting the value of V dP from equation 1, from corresponding equation, into this equation, we will get what? P dV minus gamma into P dV is equal to nR dt. Now here, the dV, that is, you can take the common here. Now if you take the common, how this equation will become? 1 minus gamma into P dV is equal to nR dt. Therefore, P dV is equal to nR dt divided by 1 minus gamma. This is equation number 6. Work done in adiabatic process is given by the general equation W is equal to integration from limits V1 to V2 P into dV. This is equation number 7. Now putting the value of P dV from the previous equation into this equation. How we will, and here we are changing the limits from volume to temperature. Therefore this equation becomes W is equal to integration from the limits T1 to T2 nR dt divided by 1 minus gamma. Now after simplification, this is nothing but you have to take the constant outside the integration. Therefore W is equal to nR divided by 1 minus gamma from integration in limits T1 to T2 in dt. Now this is, that is, W is equal to nR divided by 1 minus gamma into the bracket T2 minus T1, which is equal to, that is the final equation, W is equal to nR divided by 1 minus gamma into the bracket T2 minus T1. When T2 is greater than T1, W max is negative because 1 minus gamma is negative. That means work is done on the gas. Now second condition is when T2 is smaller than T1, W max is positive, that is work is done by the gas. Part of this chapter is Joule-Thomson effect. According to Joule and Thomson, when a compressed gas is forced through porous plug into a region of low pressure, there is an appreciable cooling. Means what is actual Joule-Thomson effects here? When a real gas at a certain pressure expands adiabatically through a porous plug or fine hole into a region of low pressure, it is accompanied by cooling. Now this effect is known as Joule-Thomson effect. Now see here, now during this, the cooling effect is due to whatever this in the Joule-Thomson effect cooling is going on, that cooling is due to the decrease in the kinetic energy of gaseous molecules. Now Joule-Thomson effect is very small when gas approaches ideal behavior. That means in case of ideal gases, Joule-Thomson effect is equal to 0. See, next part is Joule-Thomson coefficient. Now this Joule-Thomson coefficient is represented by the symbol mu to the base Jt. Jt refers for the Joule-Thomson. Now consider an insulated tube fitted with porous plug. This is an insulated tube fitted with porous plug in the middle and two frictionless piston A and B at both the sides. Let V1 be the volume of gas at pressure P1. Let V1 be the volume of gas at pressure P1 be forced through the porous plug by the movement of piston A. The gas in the right hand chamber is allowed to expand to V2 and pressure P2 by moving the piston B outward. The change in temperature is found by taking readings on the thermometer, that is T1 and T2. The work done here, the work done on the gas at piston A is P1V1 and the work done by the gas at piston B is P2V2. Therefore, the net work done by the gas W is equal to P2V2 minus P1V1. Now, from the first law of thermodynamics, you know the mathematical equation of first law of thermodynamics, delta E is equal to Q minus W. But the process, whatever the process we have considered, that process is adiabatic. That means Q is equal to 0. In the first law equation, delta is equal to Q minus W. If you substitute Q is equal to 0, this equation will become delta E is equal to minus W. And you know what is delta E? That is nothing but E2 minus E1. And here you substitute the value of net work done, that is which is equal to minus into the bracket P2V2 minus P1V1. Now, if we just rearrange this equation, we will get E2 plus P2V2 is equal to E1 plus P1V1. Now, what is this E2 plus P2V2? You know the definition of enthalpy, mathematical definition of enthalpy is E plus PV. H is equal to E plus PV. Therefore, this is E2 plus P2V2 means it becomes H2. And this is E1 plus P1V1 means it becomes H1. Left hand side is H2 and right hand side is H1. Therefore, this enthalpy H2 is equal to H1. That means if we take this side, it will become H2 minus H1 is equal to 0. That is delta H is equal to 0. Thus, adiabatic expansion of a real gas occurs not with constant internal energy but with constant enthalpy, and this is called as isoenthalpic process. Enthalpy is a state function taking temperature and pressure as independent variables. Therefore, enthalpy is nothing but the function of temperature and pressure. Now, if you differentiate this, we will get dH is equal to del H over del P at constant temperature T into dP plus del H over dt into dt. Now, in Joule-Thomson effect, enthalpy remains constant means dH is equal to 0. We can substitute dH is equal to 0 in this equation too. Therefore, how this equation become? Del H by del P at constant temperature into dP plus del H by dt at constant temperature into dt is equal to 0. This is equation number 3. Putting this equation throughout by dP and imposing the condition of constant enthalpy, therefore how this equation become del H over del P at constant temperature plus del H over del T at constant pressure into del T over del P at constant enthalpy is equal to 0. This is equation number 4. But in this equation, we know what is this? Del T over del P at constant enthalpy is nothing but Joule-Thomson coefficient, which is represented as mu Jt, and del H over del T at constant pressure is nothing but Cp, that is the heat capacity at constant pressure. If we substitute these two values in equation number 4, now how this equation will become? Now see here, this equation will become del H over del P at constant temperature plus mu into Cp is equal to 0. Therefore, mu is equal to minus 1 divided by Cp into the bracket del H over del P at constant temperature. Part is Kirchhoff's law. Now see, what is this Kirchhoff's law? In Kirchhoff's law, it shows the relationship between variation in heat of reaction with temperature. Now let us know the statement of Kirchhoff's law. Kirchhoff's law states that the change in the heat of reaction at a constant pressure for every degree change of temperature is equal to the change in the heat capacity at constant pressure accompanying the reaction. This is the statement of Kirchhoff's law. Now, to know the explanation about Kirchhoff's law, let us consider a general reaction A gives B. Now see here, suppose heat of reaction, that means heat evolved at a temperature T1 is equal to delta H1, and the heat of reaction, that is also heat evolved at temperature T2 is equal to delta H2. See, next is, now this is the diagramical Kirchhoff's law. Now the process is going on from A to B, and the heat evolved is, that is delta H1 and delta H2 at temperature T1 and at temperature 2. Now the same process follows two paths. This is path 1 and this is path 2. Now let us discuss here. Now starting from A, at a temperature T1, we can reach B at temperature T2. Therefore, in case of first path, now in first path what happens? Allow the reaction to take place at T1 and to obtain the product B at a temperature, and heat this up the reaction at temperature T2, then heat evolved in the first stage is equal to delta H1, and heat absorbed in the second stage is equal to CPB within the bracket T2 minus T1. Now here in this equation, what is CPB? Now CPB is average molar heat capacity of the product. Now the net heat evolved is equal to delta H1 minus CPB within the bracket T2 minus T1. Second path, now heat up the reaction at temperature and allow to reach the final product. Now see here, that is heat absorbed in the first stage is equal to CPA within the bracket T2 minus T1. Now here, what is CPA? This is the average molar heat capacity of reactant A. Now heat evolved in the second stage is equal to delta H2. Therefore net heat evolved is equal to delta H2 minus CPA within the bracket T2 minus T1. Initial and final states are same in both the cases, whatever the cases we have discussed just now. Now therefore, by law of conservation of energy, we must have the net heat evolved by path 1 is equal to net heat evolved by path 2. We know the equation of net heat evolved during path 1, and we know the mathematical equation to the net heat evolved by path 2. You substitute these two values in this equation, we will get delta H1 minus CPB within the bracket T2 minus T1 is equal to delta H2 minus CPA within the bracket T2 minus T1. If we rearrange this equation, we will get delta H2 minus delta H1 divided by T2 minus T1 is equal to delta Cp. Inversion temperature. Now see, before going to discuss about inversion temperature, this inversion temperature depends upon the Joule-Thomson coefficient. Now see, every gas has a definite temperature at particular pressure at which mu is equal to 0. Means below this temperature mu is equal to positive and above this temperature mu is equal to negative. Means now we can define the inversion temperature. See, this temperature at a particular pressure at which mu is equal to 0, that means the gas neither be cooled down nor heated up on adiabatic expansion is called the inversion temperature. One is bond energy and bond dissociation energy. Now see here, what is bond energy? The bond energy of a particular bond is defined as the average amount of energy released when 1 mole of bonds are formed from isolated gaseous atoms, or the amount of energy required when 1 mole of bonds are broken so as to get the separated gaseous atoms. For example, this is the gaseous molecule. When we break this, we will get the separate gaseous atoms. These are the free radicals. Across with the different molecules, the molecules like diatomic molecule and polyatomic molecule. So, in case of diatomic and polyatomic molecule, how this concept related, that is bond energy or bond dissociation energy. Now see here, for diatomic molecules like hydrogen and HCl, etc., the bond energy is equal to the bond dissociation energy of the molecule. Now, but for polyatomic molecule like methane, the bond dissociation energies of the 4 CH bonds are different. Therefore, in such cases, you have to take the average value. How it is, that I will show you. From this example, that is in methane, all 4 CH bonds are equivalent, but the energy required to break the first bond, that is here, from CH4 we can break first hydrogen bond, now is not the same as the energy required to break the second bond, that is from this we can break the second bond and so on, other bonds. Now that means the individual dissociation energies of 4 CH bonds is found to be different. Now that is different, that means in methane, ethane and propane, etc., that is bond dissociation energy depends upon nature of the rest of the molecules. The example is water molecule. Now in water molecule, see water molecule, how much the bond dissociation energy, delta H is equal to 926.49 kilojoule per mole. Now here energy required to remove first hydrogen bond from water molecule is 490 kilojoule per mole, that is the dissociation energy for this HO and H bond. Now similarly, energy required to remove the second hydrogen atom from water molecule is 426 kilojoule per mole, that is nothing but the dissociation energy D to break the OH. Now therefore, but average bond dissociation energy to break both OH bonds in water molecule is equal to, you have to take the average. You know the net value 926.98 divided by 2, that gives the average bond dissociation energy, that is 463.49 kilojoule per mole. This completes our first law of thermodynamics chapter.